Hello, my wonderful honor students. It's time to talk about math with series and parallel separately. So this video with your notebook out is going to be all about what we kind of did in class in terms of setting up the tables, how to understand and how to apply it. So the whole basic idea is we're going to use Ohm's law, V equals IR. And if we need to in the future, we'd use power as well. And this table with the total at the bottom is to be our approach to understanding what happens in a circuit. So let's find the voltage and current for all. Draw this little circuit right here. The first thing I'm going to do is write down everything I know. I know the total voltage is 25, and I know each individual resistance as well. And then by drawing my current arrow, I see there's no junctions here, so they all have the same current I, which means that this is a series circuit. So the first thing I know with series circuit is to find the total resistance by adding them all up. I get 232, so I put it down here in my table. The next thing I want to do, obviously, because I have two things in the total and only one thing unknown, ignoring power, even though I could find power from V squared over R or V times I or I squared R, whatever, I'm going to find the total current. Using the total values, V equals IR, I get the total amps to be 1.077. And that goes through each one because they all have the same flow, because they all have the same current going through it because of my arrow. I'm going to put that in for I. And for the current through, we just said they're all the same, so I'm going to put it in for each one. Now at this point, we found the current for each one. We could easily find the voltage. And to do that, I'm going to do the math for each one. You can see how math is going to go across the table, and assumptions kind of go up. I'm going to use V equals IR for each one, and I get these different values. Please notice, like we said in the last video, the more resistance something has in a series, the harder it is to get the same flow. So you need more push, which is volts. Notice how the highest voltage is at the highest resistance. Two things that are almost the same resistance have almost the same voltage, just the one that's a little bit more is a little bit more. And the 10 ohms, which is by far the smallest, has by far the least voltage. I could also check my answers to make sure they make sense. Since in a series circuit, the voltage kind of splits up among each one, if I add all these voltages up, I better get the total voltage of 25. And that's how we do a series circuit. If you want to try to find power, again, you can find power for the total or for each one. You can just do V times I, these first two, get the power, get the power, get the power, get the power, and that should equal the total power. So we did the same thing, we're find voltage and current for all, but look at this one. This looks a little weird. Well, I know the total voltage is 25. I wrote down each individual voltage as well. And I'm going to draw my current arrows. And this is kind of wacky, so I apologize. But the total current starts up here. Here's a junction. Some goes through the top path, which is just one resistor, till it reaches here and goes back to the start. The next path, it goes through one resistor, and again goes back to the start. One resistor, back to the start. One resistor, back to the start. So this is technically a parallel circuit with 4 separate parallel paths. And since each path has only one resistor, each resistor is parallel to each other. So don't freak out about pictures, but if you draw your current arrows and think about it logically, you've got yourself a ball game. To find the total resistance, the whole 1 over thing. 1 over the total resistance is 1 over the first plus second plus third plus fourth. So when I do the right side mathematically, I get 0.14098, and I do 1 over that to get REQ, I get 7.0928. That's my total resistance. I'm going to put it in right here. Just like last time, next is to find the total current, V equals IR. And I get 3.52 amps. Notice with the same resistors, you get a heck of a lot more current in parallel than series. Now instead of finding the current for each one, instead of saying the current's the same, we know the current splits up. But what doesn't split up is the voltage then. Since these all connect the same high and low points, and since the voltage can't split if the current splits, we could say they all have the same 25 volts there. Notice again, my assumptions go up the table, my methods go across. So we found the voltage for each one. Now we got to find the current. To find the current, we're going to do V equals IR, using the same numbers. V and R gets I. And as my check, I'm going to make sure all these add up to be the total current, and they do. And notice here, unlike series, the more resistance, the less flow with the same volts. And again, if you want to find power, you can do the math to the side as well, and it works out. So here's an example of series and parallel, the assumptions, the math, and how they kind of tie in together. I look forward to teaching you.